Let's explore the convergence of the following infinite series. The series can be expanded as follows. This is an infinite geometric series. With a first term of ones and a common ratio of x, since the absolute value of the common ratio is less than 1, this infinite geometric series converges, and its sum is given by a over 1 minus r, which is equivalent to 1 over 1 minus x. Similar to the infinite geometric series we saw earlier, the power series takes the form where the power of x becomes a whole number. Here, x is the variable, and an is the constant coefficient. If all an are 1, the power series takes the same form as the infinite geometric series we saw earlier. It converges when x is greater than -1 and less than 1, and diverges otherwise. The convergence or divergence of the power series depends on the value of x. When the series is in the form of x minus c raised to a power, it is called a power series centered at c. Expanding this, we get a polynomial function, so let's define it as px. The first derivative is as follows. The second derivative follows a similar pattern. Let's also find the third derivative. Add x equals c. Then p of c is a0. X minus c term is 0 for all terms. The first derivative of p at c is a1. X minus c term is 0 for all terms. The second derivative of p at c is 2 times a2. X minus c terms are 0. The third derivative of p at c is 2 times 3a3. X minus c terms are 0. If we define the function px as an arbitrary function f, then a0 is f of c, a1 is the first derivative of f of c, a2 is the second derivative of f of c over 2 factorial, a3 is the third derivative of f of c over 3 factorial. Applying this relationship to the function px, we get the following function expression. This is called the nth Taylor polynomial for f at c. If c is 0, a simpler form of the function expression is obtained. This is called the nth Maclaurin polynomial for f. The Taylor polynomial and Maclaurin polynomial are defined when an arbitrary function is differentiable up to nth order. Let's look at the following example. Construct a fourth-degree Taylor polynomial for the sine function at c equals pi over 6. Since c equals pi over 6, the sine value is 1/2. The first derivative is the cosine function. The cosine value is square root of 3 over 2. The second derivative is the negative sine function. It is -1/2. The third derivative is the negative cosine function. It is negative square root of 3 over 2. The fourth derivative is the sine function. The sine value is 1/2. Substituting coefficient values into the previously expanded Taylor polynomial, we get the following fourth-degree Taylor polynomial. When graphed, we can observe that around the value of c, the polynomial provides a very close approximation. But as we move away, the disparity increases significantly. Let's examine the graph more closely. The given function and the Taylor polynomial coincide at c and are very close around it. The f of x is represented by the black graph, while the Taylor polynomial is represented by the red graph. Let's solve another example. Construct a sixth-degree Maclaurin polynomial for the function. The given function is the cosine function. The first derivative is the negative sine function. The second derivative is the negative cosine function. The third derivative is the sine function. The fourth derivative is the cosine function. The fifth derivative is the negative sine function. The sixth derivative is the negative cosine function. F of 0 is 1. The first derivative of f of 0 is 0. The second derivative of f of 0 is -1. The third derivative of f of 0 is 0. The fourth derivative of f of 0 is 1. The fifth derivative of f of 0 is 0. The sixth derivative of f of 0 is -1. We eliminate all terms with coefficients equal to 0. Substituting coefficient values into the previously expanded Maclaurin polynomial, We get the following 6-degree Maclaurin polynomial. See you next time.